the organizers for the invitation, and particularly the local organizers for the very nice accommodation. The title of my talk is on a class of quotient spaces of moment-angle complexes. So this is our plan. So first I introduce the background and review some known results on this topic, and then I will introduce the main results. Then I talk about the applications of the main results. In the fourth part, I will give you some idea of the proof. It is just a very brief outline, and then I will talk about some generalizations in the end. So first of all, this is a definition of moment-angle complexes, which has been introduced by many speakers before. So for simplicial complex K and on a vertex set M and a pair of spaces, we can construct a topological space XAK in the following way. Notice that the building block of the space is a product of spaces. Right? The building block is this, XA sigma, where sigma is a simplex of K. So this is the reason why people call it polyhedral product or generalized moment-angle complex. In particular, when XA is D2S1, this is called the moment-angle complex of K. And if XA is D1 and S0, this is called the real moment-angle complex of K.
Actually, when it's generalized moment-angle complex, when it's big disk and big sphere.
Oh, okay. Oh, I see what you mean. Okay. But this definition can be generalized even, right? But originally, these spaces are introduced by Davis and Yanskevich in 1991 in a slightly different way. So let PK denote the cone of the barycentric subdivision of the simplicial complex K. And then any K minus 1 simplex determines a subcomplex F sigma. Then the polyhedron PK, together with this decomposition into these faces, F sigma, is called a simple polyhedral complex. And Davis and Yanskevich define this space using a coloring of the vertices of K. So a map is called a Z2R coloring of K if it's just a map from the vertex set of K to Z2R. And similarly, ZR coloring is a map from the vertex set to Z to the R. So because we will discuss the quotient space of moment-angle complex and the real moment-angle complexes at the same time, so I introduce these two notations. And this is a basic construction. For any coloring of the vertex set of K, then we can define a space in this way. So xk lambda is pk, the simple polyhedral complex, times z2 to the r, and under this equivalence relation. Here, pg and p prime g prime are equivalent whenever p prime equals p in some f sigma, and the difference between g prime and g is in some group G lambda sigma, where G lambda sigma is defined in this way. So G lambda sigma is a subgroup of Z2R generated by the set of, you can think of this as colors, right? Generated by the set of colors. And the G capital lambda sigma hat is the torus subgroup of TR corresponding to the subgroup of ZR generated by the colors by the colors of sigma. So these are quite standard basic construction. And so you see from any such kind of colorings, right? So for because there's no restriction of the coloring. So for any such kind of colorings, we can construct such a space. And in particular, if we color the vertices by basis of Z to M, where M is the number of vertices of K, then this construction gives us the real moment-angle complex and moment-angle complex. And we denote the corresponding quotient maps by pi k and pi k hat. And in this construction, and in this construction, we have a natural, a canonical action of Z to M on the real moment-angle complex K, and a canonical TM action on the moment-angle complex of K. So in this way, so this is quite natural action. So I call it canonical action. Here there are some known results on moment-angle complexes. So first, this is by Bushtaber and Panoff. The cohomology ring of moment-angle complex of K is isomorphic to the Tor algebra of the phase ring of K, where the phase ring is defined this way. I think many speakers has talked about this before. But the remark is there's no analogous isomorphism for the cohomology ring or for the real moment-angle complex of K. I mean the ring structure. I mean, but for the if you just want to compute the cohomology group, then this kind of formula can also compute the cohomology group. But the ring structure, there's no such kind of isomorphism for real moment-angle complex.
Isn't there one additively?
Yeah, additively this is for the real moment-angle complex. Additively is also true, but just the ring structure doesn't correspond to the ring structure in the Tor algebra. And second, from the Tor algebra, we have this Coxeter's formula, which can help you to compute the cohomology groups of these spaces very easily. So by this formula, the q-dimensional cohomology group of this space is equals equals the sum of the q minus 1 or q minus j. This means the number of elements in J, minus 1. Cohomology groups of Kj, where Kj is the full subcomplex of K obtained by restricting to the subset J. So J is the subset, a subset of the vertex set. So Kj is a full subcomplex of K restricting to J. So we can compute the cohomology groups of this space via the cohomology groups of the subcomplexes, full subcomplexes of K, in this way. And actually, this results also follow from the stable decomposition of these spaces. So this is a result by Professor Bali, Bandersky, Cohen, and Gittler. And they show that there are homotopy equivalences between the suspension of real moment-angle complex of K and the big wedge of the double suspension of Kj. And for the moment-angle complex, this is the suspension of moment-angle complex is the wedge of, this is J plus 2 times suspension of Kj. Okay. So, and it's very easy to see that this isomorphism actually follows easily from this homotopy equivalence. Okay. And in this talk, I want to talk about the quotient spaces of real or moment-angle complexes. So for a subgroup H in this Z2 torus or the real torus, so we have quotient spaces where H and H hat acts on real moment-angle complexes and moment-angle complexes through the canonical actions respectively. So and the study of such kind of quotient spaces are mainly, I think, so far mainly done when K is a simplicial sphere that is dual to a simple polytope. So suppose Kp is a simplicial sphere that is dual to an n-dimensional simple convex polytope with m facets. And then Zp is called the Mohm-Nango manifold, and Rzp is called the real Mohm-Nango manifold. And if a group H is Z2 m to the n, so m is the number of facets, n is the dimension, it can act freely on the real Mohm-Nango manifold, then through the canonical action, then the quotient space is called small cover. And similarly, if a subgroup of rank m minus n, this is a subtorus of m minus n, can act freely on Mohm-Nango manifold through the canonical action, then the quotient space is called a quasi-toric manifold over P. And these manifolds are introduced by Davis and Jankowicz in the 1991 paper, and they systematically studied the properties of these spaces. And many topological properties like cohomology groups, characteristic classes of these spaces are known. Okay. In addition, there's another work on this topic. So for general subtorus of Tm, which act freely on Zp, then Buchtaba and Panoff show that there's an algebra isomorphism between the cohomology ring of the quotient space and some Tor algebra. Here, this is a phase ring of Kp, but it is equipped with some twisted module structure determined by the subtorus. So this is a generalization of their theorem on the Mohm-Nango manifolds. But this result is for Mohm-Nango quotient space of Mohm-Nango manifolds, not the real Mohm-Nango manifolds. Okay, and next I want to give you some idea of what I'm going to talk about, because in my talk I will talk about a special class of quotient space of real Mohm-Nango complex and Mohm-Nango complex. So here you can see that I draw this is the boundary of a hexagon. Okay, so this is a simplicial circle with 6 vertices, and if I color the vertex V1 to V6 by a basis, say E1 to E6, then we get Mohm-Nango manifold of this simplicial complex. But if we only use less colors, say I only use E1, E2, E3, and E4, and I consider this as a basis of Z24 or Z4. Okay, so if I consider this as a basis of this, I only use these 4 colors to color the vertex, and then we can get some space, right? In addition, each color actually, any such of coloring actually determines a partition. Say the number, the vertices that's colored by E1 is say V1, V5, and colored by E2 is V6, colored by E3 is V4, V6. E3, V4 and V2 and V4, and those vertices colored by E4 is V3. Okay. So this kind of coloring actually is encoded by this partition of vertices. Okay. So essentially, the space we obtained from this coloring is determined by the partition of the vertices. Okay, and the space we obtained can be thought of as a quotient space of the Mohm-Nango complex or real Mohm-Nango complex. So in general, we have this definition. Say let alpha be a partition of Vk, and partition means alpha 1 to alpha k are disjoint subsets of the vertex set of k, and their union is vk. So this is a partition. And let lambda alpha, this is a z2k coloring of k defined by and this map color every vertex belong to alpha I by ei, where e1 to ek is a basis of z2k. So here k could be less than the number of vertices of k. K could be less than m. And similarly, the capital lambda alpha is defined in this way. So from these two coloring, we obtain two spaces, xk lambda alpha and xk capital lambda alpha, which are essentially determined by the simplicial complex k and the partition alpha, right? And in particular, when alpha is a trivial partition means each set consists of only one vertex. Then this is nothing but the space is nothing but the real moment angle complex and the moment angle complex. Okay. So this is example. So this is the boundary of a 2 simplex. So we can just color its 3 vertices by the same color, say E1. Okay. So the space we obtain is a 2-dimensional sphere. And for this one, so this is the picture I draw here. So this is the boundary of a hexagon and a hexagon, and this picture gives us a close connected orientable surface of genus 5. Okay. And for this picture, we can compare this with so we can compare this picture with the moment angle, real moment angle complex, say. So this one is, we know this is a sphere too, right? The real moment angle complex of the boundary of a 2 simplex is also a sphere. And the picture looks like this. So this is 8 copies of triangle glued together, and we get something like this. So we have 8 triangles glued together, we get S2. And this one actually is also S2. But this S2, when we draw it, I mean, some people like to think of it as an orbifold. So I think we should probably draw it in this way. And this this one topologically is also S2. But you can think of it as it's just gluing of 2 triangles along their boundaries. So it has three cone point. But this one has only two cone point. Okay. So all these spaces are the spaces defined by some partition, right? Okay. Now we can say something about the cohomology groups of such spaces. So for any simplex sigma, so let's define some notation. We define the rank sigma is just a number of vertices of sigma. It equals the dimension of sigma plus 1. And we define the I alpha sigma. So I alpha sigma is the index I in K, so that V sigma is the vertex set of sigma. Intersect with alpha I is non-empty. If we think of K as the set of colors, then I alpha sigma is the set of colors that are used to color sigma, right? So this is this is just a palette that used to color sigma. And for any subset L in this in the set of colors, so K you can think of it as a set of colors. L in K, then we define K alpha L is a subcomplex of K consisting of those simplices whose color with I alpha sigma belongs to L. It means the colors of sigma belongs to the set L. So you can think of this as a subcomplex of K defined by a set of colors. And our theorem is this: for this kind of quotient spaces of Monod-Nangle manifolds or real Monod-Nangle complexes, the cohomology groups actually can be computed in a very similar way as the Coxeter formula. So the cohomology is the sum of the cohomology of this kind of subcomplexes of K, where L ranges over all the subsets of K.
Excuse me. Did you give an example of one of these which is not a generalized moment-angle complex?
Because like small covers and
No, but in anyone, is there?
many small covers and like quadratic manifolds there.
So it's small covers. You have examples of these manifolds which are not generalized moment-angle complexes.
Yeah, I think conceptually they are not. So like, say. I think such kind of things. I mean, small covers that which can colored by basis of, let's say, Z2 to the
What
n.
is the smallest example of one of these? Smallest example which is not a generalized moment-angle complex.
I think
here, I think that's it defines the generalized color.
Well, I'm just saying, what is the first example? The first example of this space.
But he also gives small cover is not a generalized moment-angle complex, right?
yeah.
Any partial quotient of the moment-angle complex is his example.
Yeah.
I'm sorry, any what?
Any partial quotient, including small cover.
Oh, I see.
Yeah. So like many small covers are not.
If you choose
I see.
choose the color,
I see. I beg your pardon.
Yeah.
I see what you're saying.
Okay. So you can see that when alpha is a trivial partition, then K alpha L is nothing but, when alpha is a trivial partition, then K is just the set of vertices of K. Then K alpha L is just the full subcomplexes of K that restrict to L, right? So this formula generalizes the Coxeter formula. Okay, so this is our first theorem, and this theorem is completely parallel to the theorem to the Coxeter formula for the cohomology groups of Monod-Nangle complexes. And in addition, we have the similar stable decomposition of these spaces. So the suspension of xk lambda alpha is the wedge of double suspension of k alpha L, and similarly we have this homotopy equivalence between suspension of xk capital lambda alpha and this wedge, and so the theorem 1. So theorem 1 actually also follows from this stable decomposition, but the ring structure of these spaces, at least not so obvious from this theorem. So we have to discuss it using some other tools.
But you can in a moment-angle complex case.
Yeah.
The ring structure.
Yeah. So I think probably some of the strategies using to understand the ring structure of the Monod-Nangle complexes can also be used to understand such spaces, because many properties of such spaces are very, very similar to Monod-Nangle complexes. So to understand the ring structures, we separate into two cases. So the first case is called non-degenerate. So a partition is called non-degenerate. It means the I alpha sigma. So for any simplex sigma, the number of elements in the I alpha sigma equals the rank of sigma. And it means the colors on different vertices of sigma are colored by different color. So this is basically what it means. So in particular, the trivial partition is always non-degenerate, because for the trivial partition, the color of all the vertices are different. And it's easy to see that a partition is non-degenerate. It means its coloring is non-degenerate. Coloring is non-degenerate also is also called characteristic function sometimes, right? Okay. So for the non-degenerate partition of the vertex set of K, then with respect to some properly defined multigradings, we have the isomorphism of Z2 modules from this to the Tor algebra, and there's an isomorphism of multigraded Z2 algebras from this space to the Tor algebra. Here the Z2 U1 to UK module structure and this is a phase ring over Z2. On this phase ring is given in this way. Say a U1 is an act on this algebra, this polynomial algebra by think of it as the sum of the generators that belongs to alpha I. So this is the ring structure of Z2K over Z2 U1 to the UK. So this ring structure, of course, is also defined by the partition alpha. Okay. Say in this picture, you see this is a non-degenerate coloring, right? Because for any simplex, the vertices are colored by different colors. But this one is not a non-degenerate. So these two are not non-degenerate. So for the general case, to describe the ring structure of their cohomology, I think probably the Tor algebra is not enough. So in general, we have to introduce some more general algebra to compute it. First, we notice that the phase ring can be defined in this way. I think some other speaker also introduced this notion. And I think Anton's talk, he also introduced this way of defining phase ring. The phase ring can be sort of generated by V sigma, where sigma is any simplex in K, and quotient out by some ideal generated by the elements of this form, where sigma this is wedge tau denotes the maximal common phase of sigma and tau, and sigma, this V tau denotes the minimal phase that contain both sigma and tau. And if there's no simplex contain both sigma and tau, and this is 0. Okay, so this is an equivalent way to define a phase ring of a simplicial complex. But actually this definition also works for simplicial posets. And now I define the algebra that are used to describe the ring structure of these spaces, of a cohomology ring of these spaces. Say we define a differential d alpha on the tensor of exterior algebra with the phase ring in this way. The d alpha ti is the sum of the generator Vj such that Vj belongs to this set alpha I. So this is the same as before, but this one is quite different. This one says d alpha V sigma is the sum of generator V omega, where omega has the same color set as sigma with one dimensional higher. So you can see that this kind of thing doesn't happen when the partition is non-degenerate, because if a partition is non-degenerate, then when the dimension omega is higher than sigma, its color set is strictly bigger than than sigma. But here, when the partition is in general, it may not be non-degenerate, then this kind of differential may occur. So in particular, say d alpha is 0 on K on the phase ring if and only if alpha is non-degenerate. Okay. So this is a theorem for the general partition. So for the general partition, then there's an isomorphism of multigraded Z2 modules from the cohomology group of xk lambda alpha to the cohomology of this algebra with respect to the differential d alpha we just defined, and for xk capital lambda alpha, and there's an isomorphism of multigraded Z2 algebras from this to this algebra. And when alpha is a non-degenerate partition, we notice that this one is exactly the Tor algebra, because when because when alpha is if d alpha is 0, then d alpha v sigma equals 0, then and this differential coincides with the differential in the Koszul resolution of the phase ring. So when alpha is non-degenerate partition, then this is just the Tor algebra. So theorem 3 actually is a corollary of theorem 4, right? So this is the more general form of computing the cohomology groups and cohomology rings. Okay, and next I will talk about some applications. First of all, in Davis and Jankiewicz's paper, he defined what is called the pullback from the linear model. Suppose K is a simplicial complex of dimension n-1. It is called balanced if there is a n-coloring of K. It means we can color the vertices of K by n different colors such that the neighboring vertices, the color of the neighboring vertices are different. So this kind of simplicial complex is called balanced. And suppose E1 to En is a basis of Z2n, and then this n coloring uniquely defines a non-degenerate Z2n coloring, right? Just send the vertex V to the coloring phi, right? E phi V. Okay. So the space, and this space is called pullback from the linear model by Davis and Jankiewicz's. Another way to understand the balanced simplicial complex is it admits a non-degenerate simplicial map from K to the n-dimensional n-1 dimensional simplex. So by our theorem, by our notation, then the pullback from the linear model can be equivalently written in this way. So it's correspond to the partition, right, defined by phi. Okay. Then by our theorem 1, we can compute the cohomology group of pullback from the linear model via the subcomplexes of K. This is colored subcomplexes of K in this way. And also we have this stable decomposition of such spaces. So these are very special examples of where we can use our theorems. Another observation is this. And I found that for any real moment-angle complex or moment-angle complex of K, it can be viewed as a partial quotient of real moment-angle complex or moment-angle complex of some bigger simplicial complexes. Say this is a pentagon, and with respect to this coloring, we have a real moment-angle complex. But if we glue the pentagon along the face labeled by E, we get a hexagon. and we have induced coloring in this way. Okay, so we can think of this hexagon colored by only 4 colors, right? And if we glue these 4 copies of this pentagon along edge D and E, we have this octagon, and this octagon inherits a color in here, and now we have only 3 colors. But anyway, in all these 3 pictures, the faces of the polygon are colored by the basis of some torus, right? Z2 torus or torus. And then we can apply our theorem to compute the cohomology group of moment-angle complex from each of these pictures. And they gave the same answer, right? So this is a dual picture. Because there, this is a polygon, but here, this is a dual simplicial circle. And for example, I told you before that this one gives you the close connected orientable surface of genus 5. Okay, then from this picture, say from the last picture, say we can compute the first homology group of this space where the colored subcomplexes. Then say the space so this 4A are the subcomplex colored by E1, and B is colored by E2, C is colored by E3, and this ABA, this is subcomplex colored by E1, E2. This is colored by E1, E3. And this is colored by E2, E3, right? So if you count the reduced cohomology group of this, you get 3 plus 1 plus 1 plus 1 plus 1 plus 3. Okay, so you get 10. Okay, so that's the first homology group of the surface. Okay, but you see this way of computing is a little bit different from computing the cohomology group of subcomplexes of a pentagon. But they gave the same answer. And oops, okay, I have a few minutes. So this is another application. So a simplicial poset is defined by in this way, and I think people have talked about this before. So I skipped this one. So it admits a geometric realization, and which is called simplicial cell complex. And the proposition is for any simplicial complex, a simplicial poset S, we can also define a notion of moment-angle complex associated to a simplicial poset. And the proposition is actually we can understand the moment-angle complex of a simplicial poset as such kind of space, x, k, lambda, alpha, where k is some finite simplicial complex, and alpha is a partition of it. So the idea is very simple. So this is a geometric realization of a simplicial poset, and we can just stretch those things that are shared by different simplices, and we just stretch it, and then it becomes a simplicial complex, and the place where it's stretched are colored by the same color. So now this is kind of coloring is like our definition, right? So we can understand this space in this way. So then, and this is a theorem by Professor Liu and Panov says there's a multigraded algebra isomorphism from the moment-angle complex of the simplicial poset and the Tor algebra of this phase ring of the simplicial poset. And so by our proposition, then we can understand the Tor algebra of the simplicial poset in terms of this kind of algebra, because the space they represented are the cohomology group are homotopy equivalent. So there's an algebra isomorphism between this Tor algebra and this one. So I think this is another way to understand the Tor algebra of a Tor algebra of the phase ring of a simplicial poset, because we use a simplicial complex. Okay. I think I have no time. I'm sorry. So because I want to, well, this is a very rough idea of how this proof goes. I explained the difference between this and the moment-angle complex. So the basic building blocks of polyhedral product is a product of spaces but the quotient space of moment-angle complexes, their building blocks are like this. Their building blocks are like this kind of thing. So it involves not only product but also like join. So I think this is the main idea, that the quotient space and this kind of quotient spaces of moment-angle complexes actually are their building blocks involve operations like Cartesian product and join at the same time. Okay. Okay, so we can also generalize our construction to, and from that viewpoint, we can generalize to this setting. So for a fixed K and a sequence of spheres, we can define a space in this way. The building blocks is like this.
That was the point that I was trying to make.
Yeah. And alpha is a trivial partition, then this is nothing but the generalized real moment-angle complex, right? Yeah. But if it's non-trivial, then this is slightly wider space. And we have the parallel theorems for all these spaces. We have this the Coxeter type formula and the stable decomposition, and they're all parallel. And also the cohomology ring structure, they're all the same.
There is essentially only one splitting theorem, and it applies. That's an application.
Yeah.
To this situation.
And furthermore, I think there's an even wider generalization. We can replace by this A1 to AK, and then we can define the similarly. And the building blocks are just join of AI with this and Cartesian product of this kind of thing. And for the trivial partition, then this is actually polyhedral product of cone of A and A. So this construction is generalization of this one.
That one has an identifiable splitting.
Yeah, and similarly, there's a homotopy equivalence between the suspension of this and this one. So we can compute the cohomology groups of this from this decomposition as well. Okay, so that's. This is the last comparison that the building blocks of polyhedral products involves Cartesian product spaces, and we have this polyhedral join introduced by Arsenberg and polyhedral smash product by Professor Barley, Bandersky, Hohen, and Gittler. So I think I think it's interesting to explore spaces with building blocks involves a mixture of Cartesian products, joins, and smash products, and they probably produce some interesting spaces, and I would expect the Coxeter type formula also hold for such more generalized spaces as well. Okay, finally, I'm sorry.